Hello, welcome to this lecture. So in this lecture, we will discuss a very important topic, which is the moment of inertia. So this is the content that we are going to discuss in this lecture. First of all, we will try to understand what is moment of inertia, what is the concept and formula for the moment of inertia, and then a very important theorem, that is parallel axis theorem. And we will see what is the procedure of determining moment of inertia of areas, and we will try to understand that with the help of two examples. Then we will talk about the moment of inertia of composite body, composite areas. Like in the previous lecture, we have tried to find out centroid of composite area, like in that way. So similarly, we will now try to find out the moment of inertia of the composite areas, and I will be showing you some moment of inertia formula for some common area, and we will see what is the procedure of determining moment of inertia of composite areas, and then we will try to understand how we find out moment of inertia of composite area by solving uh, some more example. Now, the first thing is, what is moment of inertia? Well, uh, technically, there can be so many interpretation of this moment of inertia, but first of all, we will try to understand in a very basic way what is moment of inertia is actually. For example, if I take a body, say this is a body, say this is, for example, this is a beam, and the CG or centroid of this beam is, say, here. It will be somewhere here, and the axis which passes through the beam along the length of beam, say I am naming this as, say, uh, x-axis, and the vertical or perpendicular axis, say this is y-axis, and similarly the third axis, say it is z-axis. Now, if I want to rotate this body about any of the axes, say for example, if I want to rotate this beam about x-axis, how much effort will be required for me? Or if I want to rotate this body about z-axis, will there be a difference in the effort to rotate the body about z-axis? Or if I have to rotate this body about y-axis, will there be any difference between the effort of rotating this body about different axes? So this effort is basically the moment of inertia. So, or if I take real life example, for example, sorry, say for example, I have this bottle. Now if I want to rotate this bottle about its horizontal axis, say like this, the effort required to rotate this bottle about the horizontal axis is different than to rotate this bottle like this. If I want to rotate this, then I have to apply more effort to rotate it. Or if I have to rotate like this, I will be required to apply more force to rotate this bottle. So this effort of applying the force or moment to rotate a body about a particular axis, this effort is basically the moment of inertia. And now we will see uh, the more interpretation of this moment of inertia in our subject, that is structural design. Now, the moment of inertia, it is basically a geometric property. It is basically a geometric property of an area. Basically, moment of inertia can be related to the mass, but here we are talking about the geometry. It can also be sometimes known as area moment of inertia. Okay. So the moment of inertia is a geometric property of an area that is used to determine the strength of structural member. So as I said, how much effort is required to rotate or to bend a body about a particular axis, that is the moment of inertia. Or in other way, if I want to rotate a beam, say for example, this is a beam. Now, because of this force, if I apply force vertically on this beam, it will bend. It will offer a resistance. So this resistance against the bending or the rotation because of this force is again a moment of inertia. Or in other words, we can say that moment of inertia is the measure of the tendency of the object to resist change in motion. Yes, moment of inertia is again related to angular motion also, because as I said that if there is a body and if I want to rotate this body about say this axis, say this is x axis, sorry, this is say y axis. If I want to rotate this body, then you can see uh, there will be angular motion. There will be angular motion of this body when it will be rotating. So higher the angular motion, sorry, higher is the angular acceleration, lower will be the moment of inertia for the body about that particular axis. So now we will see how do we find out moment of inertia of any body about any particular axis. Well, theoretically, if I say that how can we calculate moment of inertia, then it says it is basically the product of elemental area and square of the perpendicular distance between the centroid of area and the axis of reference is the moment of inertia about that reference. For example, now here if I take, say this is a area, and if I want to find out moment of inertia of this area about this axis, say this is axis y. So which means this area is will be rotating about this. If I rotate this, the area of this, I mean, if I rotate this area about y-axis, then what will be the moment of inertia, or how much effort will be required to rotate this area? And for that, what we can do is, uh, if I define, I mean, if I have to find out moment of inertia of this area, what we can do is we can divide this area into a very differential elements. Say, for example, if I take an element this, and this element is having area dA, okay, and now this element will be having its own centroid. Okay, so the distance from its own centroid to the axis, say this distance is say y1. Similarly, there may be some other element which will be having other distance or say different distance. Say this is y2. This is again a dA. So there can be so many areas, so many differential areas which can rotate about. So basically, to find out moment of inertia of the whole area, what we can do is we can write the relation. Uh, if I multiply this area once with y1, what will happen? Say, if I multiply this with y into dA, it will become moment of area of differential particle. Similarly, if I again multiply this with y with the same distance, if I again multiply this, then this becomes y square into dA. So this becomes the second moment of area of the element or particle. Now, if I want to find out this second moment of area for this whole area, then how I can find out that? By integrating it. So by integrating it, say this is the whole area. By integrating it, I can write this as y square into dA. So this becomes the second moment of area, second moment of area of the whole body about y-axis. So this becomes IY. Now, moment of this Iy is I'm representing this as second moment of area, and second moment of area is nothing but the moment of inertia. So that is how we can formulate the moment of inertia in this case. So, and that is what written here. The product of the elemental area and square of the perpendicular distance between the centroid of area and the axis of reference is the moment of inertia about the reference axis. So we can write now with the help of this diagram, we can infer that if we want to find out moment of inertia of this area about y-axis, so it can be written as Iy is equals to integral of x square into dA. dA is the area of the element. So to find out Iy, we multiply with this distance. Similarly, to find out this moment of inertia of this body about x-axis. So it means now this time this body will rotate about x-axis. So how much effort is required? So that can be quantified by using this formulation. So again, what we can do is we can again find out the perpendicular distance of the element with reference to the x-axis. So again, multiplying this area twice with this distance, we can find out the second moment of area for this body about that particular axis. Similarly, now in this case, y-axis and x-axis is shown. There can be z-axis also. Now z-axis can be, say, z-axis can be, for example, if this is the z-axis. Now from the z-axis, what will be the distance of this dA? The distance from z-axis will be r. So this r can also be written as r square is equals to x square plus y square. So with this relation, we can also write that moment of inertia about Izz can be written as uh, Ix plus Iy. Now, how it happens, you can see here. If I explain it, you can see here uh, y square into dA plus x square into dA. Now adding this, we will be getting this. So basically this theorem, this is actually a theorem which is called perpendicular axis theorem. So according to perpendicular axis theorem, the moment of inertia about z axis or the polar axis is basically the sum of moment of inertia about x axis and y axis. So this is again a theorem which is called perpendicular axis theorem. So moment of inertia is also known as second moment of area because first moment of elemental area is day, which is called moment of area. And if it is again multiplied by the distance, we get second moment of area, which is called the moment of inertia. So as I said that we can also formulate this quantity for dA about the z axis, or sometimes we call it as polar axis. So moment of inertia about polar axis can be calculated as the sum of, it can be calculated as r square into dA. So this time for z axis, the perpendicular distance of this dA is r, and r is basically, you can see here, this is y and this is z axis. So this is basically making a right triangle. Basically the distance is here. We can easily use the Pythagoras theorem, and using that we can formulate the value, we can formulate polar moment of inertia as the summation of Ixx and Iyy. So the relation is possible because r square will be equals to the sum of x square plus y square. And yes, the units of moment of inertia, as you can see here, this r square is distance and dA is again the unit of dA. Generally, area is expressed as in mm square. Similarly, the distance is in the square. So mm square into mm square, so it becomes mm to the power 4. So that is why the power here for moment of inertia will be 4. So this is a very important thing. So we will continue our discussion in the next part. Thank you.